Let's actually apply our lovely ideas of bonding and anti-bonding orbitals to some real molecules. We'll start off with H2. Now H2, of course, the simplest possible covalent species. Each hydrogen, 1s1, 1 electron. So when we draw it out, here's the 1s on one hydrogen, the 1s on the second hydrogen. We're going to get the positive in-phase overlap to give us the bonding, and the out-of-phase cancelling out overlap to give us the anti-bonding. So there's each hydrogen. Now let's bring those two hydrogen atoms together to make the H2 molecule. This H2 molecule is going to have 2 electrons in it. Both of those electrons are going to go into the bonding orbital like so. We would describe this, its MO electron configuration, very much as we did the 1s2, 2s2 back with atomic orbitals, sigma 1s, 2 electrons in the sigma 1s orbital. And we're going to start thinking about bond orders. Well, bond order is what fraction or how much of a bond do you have. A single bond has a bond order of 1. Well, a single bond has 2 electrons in it. A double bond, for which the bond order is 2, has 4 electrons. A triple bond, for which the bond order is 3, has 6 electrons. So just the bond order is obviously the number of bonding electrons you've got divided by 2, because there's 2 electrons in each bond. So H2, each hydrogen, 1s1. MO theory predicts a single bond, as does everything else. G, you say, why the fuss? Well, now let's think about He2. Say there's no such molecule, is there? Because helium, 1s2, it's happy. Well, let's apply our MO theory to the idea of He2. So again, we would say, well, we've got 2 heliums. They've each got 2 electrons in the 1s. As we bring the 2 heliums together, you're going to get the in-phase nice bonding overlap to give you sigma 1s, and the out-of-phase nasty non-overlap to give us the anti-bonding. Well, in He2, there would be 1, 2, 3, 4 electrons. 2 electrons would go into the sigma 1s, but then 2 electrons would go into the sigma 1s star. For every bit of energy gain you make by using the bonding orbitals, that gets cancelled out by the anti-bonding orbitals. The electron configuration, sigma 1s2, sigma 1s star 2, 2 in the bonding, 2 in the anti-bonding. And the way we would express that is we'd say, yes, we got 2 bonding, but we've also got 2 anti-bonding. So 2 bonding minus 2 anti-bonding cancels out to give 0. So if He2 existed, it would have a bond order of 0. Well, if there's 0 bond, then there's no molecule. Now, what has been observed under rather strenuous conditions like mass spectrometers and so on is He2+. Well, how can we explain the existence of He2+? Well, we can do that using our molecular orbital theory. Again, there's our helium with a 1s, helium with a 1s, 2 electrons in each helium, and so you would say, well, we'll just have the 4 electrons that will cancel each other out. But it's not He2, it's He2+. So that means there's only a 3rd electron. 2 go into the sigma 1s, there's only 1 more electron, the 3rd electron, because 4 minus 1 is 3, goes into sigma 1s star. So therefore the electron configuration of He2+ is sigma 1s2, sigma 1s star, 1. Bond order, therefore, 2 bonding, 1 anti-bonding, so it can exist. It will have half a bond. In other words, there's only effectively 1 electron, 1 bonding electron shared by the nuclei, but you can see why He2+ might exist, whereas He2 wouldn't. So hopefully, some nice little easy applications of our bonding and anti-bonding orbitals. Before we make it complicated, let's go to the second period, where we're just going to start talking about the 2s. And of course, the first atom in the second period is lithium. So let's think about Li2. Well, lithium has got 1s2, 2s1. So we've got to worry about not just the 1s orbitals, which will overlap just as we've seen before, but also 2s orbitals. And the 2s orbitals will overlap with each other in exactly analogous fashion to the 1s. We'll get the positive in-phase overlap to give us the bonding orbital, and it will be a sigma orbital, and then we'll have the outer phase non-overlap to give me the sigma 2s star. Exactly the same idea, except because the 2s is bigger than the 1s, the sigma 2s will be bigger than the sigma 1s. Pop in the electrons, 1s2, 2s1. We got a total of 1, 2, 3, 4, 5, 6 electrons, so 2 in the sigma 1s, 2 in the sigma 1s star, and then 2 left over to go in the sigma 2s. So Li2, sigma 1s2, sigma 1s star 2, sigma 2s2, bond order, 4 bonding electrons, 2 there, 2 there, 2 anti-bonding electrons there, give us a bond order of 1. By the way, for those of you who are Star Trek fans, you might have heard of dilithium crystals. Well, here we are, dilithium crystals. Dilithium can exist. It would have a single bond holding the 2 lithiums together. Now, a lot of times, in the same way that when we were doing the atomic electron configuration, we'd say, well, this 1s2 is so boring. We don't care about it, right? We only care about the valence electrons. Well, we can do that here if we want to, just thinking about the valence electrons. So we ignore the 1s's, therefore we'd ignore the sigma 1s and the sigma 1s star, and we would just draw it with the sigma 2s, the sigma 2s star coming from the 2s's. The electron configuration, we wouldn't even mess with the sigma 1s2, sigma 1s star 2. We just start off sigma 2s2. Does that affect our calculations? Absolutely not. Now we got 2 bonding electrons, no anti-bonding electrons, bond order is still 1. Because, of course, in the same way that when we were doing the atomic electron configurations, we said that those inner core electrons were really of not any importance. When we're dealing here with our molecular orbitals, the 2 electrons in the bonding, sigma 1s, will cancel out the 2 electrons in the anti-bonding, sigma star 1s, once we move past the 1s and into the valence shell of the 2s. I could go ahead and do beryllium as well, but that would be boring, and besides which that's one of the homework questions. So in the next movie, we'll stay in the second period, but we'll start thinking about the 2p's.